So this is the lesson for 8.3, equations of sinusoidal functions, and what we've done is we've looked at y equals sine of x, right, and y equals cos of x. And we know a lot about what those characteristics are. We know what they look like. Well, we are going to look at cosine and sine graphs again, but ones that are squished up, or the ones that are stretched out, or ones that are taller, or ones that are flipped maybe, and we're going to take a look at how the parameters of the function change what it looks like. So I want you to copy this down right here. Okay? This is the form of a sine graph. Now we've added some, we're going to talk about what a number in front of the sine does. We're going to talk about what this number right here does, what this one does, and what this one does. So I want you to write this down in your notes right there. Y equals A sine B bracket x minus c bracket plus d. Okay, just the sine one, just write that one down for now. Okay, so make sure if you're graphing calculator here, your window looks somewhat like this. And we're going to take a look at what sine looks like in this, with this window. Okay, so there's sine x, hit y equals, type in sine x, there's your variable button there, and we'll graph it. So sine x should look something like that. So with that sine graph, that's this one right here, the sine of x. Now what we're going to do is we're going to explore how different numbers change the sine graph. So for example, let's take a look at y equals 2 sine x. So on your graphing calculator, whatever you're using, okay, go to the y equals button and do this for me. Leave sine x and write 2 sine x. Just like that. You don't need to close your brackets here. You don't need to do that. And hit graph. And now watch carefully what happens. Here's the new sine graph. Okay, so we've got both of them on there at once. I understand that. But this is your original sine graph. And if you hit trace, okay, you can move your cursor along and it'll show you in the top corner which graph the cursor is on. So if you want to identify them, that's your regular sine graph. Look at the maximum point is 1. And if you hit your up arrow or your down arrow in this case, it'll go to the second function that's graphed. And this is the y equals 2 sine x. Okay? So that's what it looks like. And what's, so how would you describe this second graph? Go ahead, anybody. How is it different than the first one? Okay, it looks like it goes up to 2 and down to, okay, maybe negative 2. Okay, so a general description might be that it stretches higher and stretches lower, right? So the maximum point is larger and the minimum point is smaller. Okay? So as a matter of fact, the a value in this equation right here, the one we're dealing with here, is the amplitude. So guess what? We just put the a value as 2. So guess what the amplitude is? The amplitude is 2. Okay? So this is the other thing you need to write down here in your notes, right here, this sentence here. The value of a is the amplitude. You should have this formula already in your notes, so you don't have to write that. The value of a is the amplitude. And we've displayed that right here by trying 2 sine x. The next one is a bit tougher, okay? We're talking about the value of b here. So that's this number right here. Well, I want you to graph this one, sine 3x, okay? So the 3 now goes after the sine. So it should look like this, 3x. Okay, so go ahead and graph that. And if you want, let's take away this second one. We already know what that one does. So you can clear that and put it in here, sine 3x. Okay. Now watch carefully what's going to happen when you hit the graph button there. Now here is your original sine graph. That's the original sine graph. Between 0 and 12, we have 2 periods. Look at this one, though. Okay? Now, you can look at this 2 ways. All right? You can look at it 2 ways to see what b does. See, I changed b from over here. This really is 1 times x, right? This is 3 times x. One way you can look at this is just what it says here in the notes. The value of b is the number of cycles in 360 degrees, or 2 pi radians. So that's the first way you can look at it. Look at how many cycles I have. Now 2 pi is right here. Okay, that's 2 pi right there. How many cycles do I have? I have 1, 2, 3. I have 3 full cycles where normally I have 1. So that's the first way you can look at what the b value does. Okay? On a normal sine graph, there is 1 complete cycle in 2 pi radians. If you change this b value to 3, there are now 3 complete cycles. It doesn't change the amplitude, doesn't change anything else, just how squished it is. See, it's kind of squished up. The other way you could look at it is, you could look at it this way. The period length is 360 divided by b, or 2 pi radians divided by b. So the period length here for this graph, that's the length for 1 cycle, is 2 pi radians divided by 3. Okay? That's 2.094 radians. Okay? That's the period length. If we look back at our calculator here, okay, look at this. There is 1 complete cycle, and we're going 1, 2, just over 2 radians. I know it's really small for you to see, but it's just over 2 radians is 1 complete cycle length, and that's 2.094. So what that means is, and I'm just going to move down here, these notes will come a little bit later, but what that means is this, is that if we had y equals sine of 0.5x, what would this number mean? It means, okay, b means how many cycles, in 2 pi radians, right? How many cycles? And so if you have 0.5 as b, that means you have 0.5 cycles. Okay, so if this is 2 pi, this is what the sine should look like, right? But in this case, you only have 0.5, so it looks like this. See, there's half in 2 pi. And so really, if you have a b value that's between 0 and 1, that's less than 1, like a fraction, it means it stretches the sine graph out. So if we confirm that on our calculator, let's try that. Let's get rid of the second one. And let's type in sine of 0.5x. And so here's our sine x. Okay, there's 1 cycle. That's 2 pi right there. Look at that. The second one, there's 1 cycle spans 4 pi radians, really. See that? Only half of it can fit in 2 pi. So that means that it's stretched out. Okay, so once again, this b value means how many cycles in 2 pi radians. And if it's 0.5, that means only half of 1 cycle can fit. Okay? Questions? All right, let's keep going then. The equation of the midline. Okay, the equation of the midline, if we look at, what we're at next here, yeah. Oh, no, I guess we missed C. Here, let's go back to C. okay? The value of C, so that's this one right here, and this is a bit tricky too. B and C are a little bit tricky maybe, but C indicates the horizontal translation that's been applied to the graph of y equals sine x. So write this down. The value of C indicates the horizontal translation. So that's a left to right move. It's either left or right. It shifts it over. Okay, so let's go back to our graph. And let's leave sine of x in there. Let's clear this second one. And let's show this right here. Let's do sine of x. And let's say minus 4. Okay? That's the C value when it's inside the brackets with x there. It's either plus 4 or minus 4 or plus something or minus something. So let's see what this one does. The sine x will graph first, and then the other one will graph. Okay? So there's your sine x. And here's the other one, okay? All right. So look at this. Where is x equals 4? Let's see. Let's calculate a value of x equals 4. Here's x equals 4. Okay? So if we take a look at, all right, if we take a look at x equals 4, do you see how 4, 0, that is actually an x-intercept for this second value. So what's happened is this original sine graph right here has been shifted over 1, 2, 3, 4 units. And it starts actually here. Now the rest of this graph, you know, the sine graph continues forever in both directions. But what's happened is every point has been shifted to the right 4 units. Okay? I'm going to draw another graph here that maybe explains that a bit better, but watch this. If this is your original sine graph, okay, 2 pi units is about 6.2, right? So let's say here's 6, and so this is 3, right? So we got 1, 2, 3, we got 4, and we got 5. And so look at what happens here. With the C value, okay, it shifts it either left or right. So we'll talk about which direction that is in a minute. But it goes, in this case, it's shifted it to the right 4 units. So this point goes 1, 2, 3, and it actually starts here. This maximum point over here actually goes over here. And so it shifts, everything shifts to the right 4 units. See that? 4 units. This one, 4 units. This one, 4 units. The minimum, 4 units. End value, 4 units. Everything shifts over. Okay? So the C value talks about a horizontal shift or a horizontal translation. Okay? So that's a good question. The question was asked, you know, how far would we have to shift the, you know, one graph to make the other one? Well, we talked about last section that it's a 90-degree shift, and when they start to look exactly alike. So if the cosine graph shifts over 90 degrees to the right, then it looks exactly like the sine graph. So we can do that quickly. Let's take a look at that. So here's the sine graph. So let's clear this, and let's make that cos graph shift 90 degrees to the right. Okay, so this is really important. If you want the graph to move to the right, you have to show this as a minus. Okay, it's got to be minus there. So this is where it's a little bit opposite. A shift to the right is a minus inside the brackets here. And yes, we're in radians right now. Our mode is in radians. So what is 90 degrees in radians? Who remembers that? About 1.6, okay? Or exactly, it's exactly pi divided by 2, yes. Okay? So if we do this, that will shift the cos graph to the right pi over 2. And if we did this right, the two graphs should be the exact same. So once this is finished writing, Yeah. See, the other one's not